All right, we should know how to name and draw alcohols. Now we'll just look at a couple physical properties of alcohols. So first off, the hydroxyl group is very polar because of the hydrogen bonding, okay, which makes small alcohols polar. Alcohols are more soluble in water than alkanes because, again, the hydrogen bonding making it polar. So alcohols with 1 to 4 carbons are soluble, but if they have 5 or more, they become not soluble because the non-polar properties take over. So as a hydrocarbon chain becomes longer, the non-polar characteristics supersede the polarity of the hydroxyl group, and the alcohols become less soluble in water. The hydroxyl group also allows the alcohols to hydrogen bond with one another. Therefore, the boiling points of pure alcohols are much higher than those of the corresponding alkanes. So as alcohols become more branched, there is less surface area, making them more soluble than long chain alcohols. And just kind of a summary of what we just talked about. Okay, moving on to the next functional group is the carboxylic acids. Okay, so a carboxylic acid is a compound that contains a carboxyl group. Okay, or it'll end in COOH. Okay, that's our carboxyl group. So carboxylic acids are weak acids for which the ionization equation can be written as, so we have our carboxyl group, and this is attached to a chain of carbons. Again, it's going to produce, this H is going to detach, become on its own, and then it'll have that COO minus on the end. Okay, so naming and drawing carboxylic acids. So notice that there are 3 bonds on the carbon atom in the carboxylic acid group are bonded to other atoms in the group, and there's only 1 position available on the carbon atom to bond to other atoms. So really, this carbon's already got the 3 bonds, as you see, 2 to oxygen, 1 to another oxygen, and then this oxygen's also bonded to that hydrogen. So really, there's only 1 spot for this chain to come off, for a carbon-carbon chain to come off. Okay, and so this carbon that's bonded here is always your carbon number 1. So when you're identifying your longest chain, you're looking, it's going to come off of this carbon. Okay, so again, you're identifying the root, identify the suffix. Okay, so we're going to drop the E at the end of the name and replace it with oic acid. We don't have to say where, so we don't have to say like butan 2 oic acid or anything like that, because this can only come off the first carbon. And so it's always just going to be oic acid at the end. You don't have to put a number. Okay, and then prefix, so any alkyl groups, okay, or branches that come off, okay, we just number them like we always have. Okay, and so the example here, we have a carbon, this is our carbon number 1. So we always find that first, and then we have, so it's 1, 2, 3, 4, 5. So we have a 5 carbon chain. So it's going to be pentanoic acid. And then coming off the 3rd carbon is our methyl group. So we get 3 methyl pentanoic acid. Okay, so some more examples here. What is the IUPAC name for this carboxylic acid, which has unpleasant rancid odor? So this, here's our carbon bonded to the 2 O's. So this is our carbon number 1. So 1, 2, 3, 4. So it's just going to be butanoic acid because there's no groups, no branches coming off. Okay, here write the IUPAC name and the full structural formula for propanoic acid. Well, the IUPAC name here is propanoic acid. Okay, and then the full structural formula, it's going to have 3 carbon chain. And then off the last carbon, we're going to have a double bond to an O. Nice O there. Single bond to an O, which is bonded to an H. Okay, and then these will just fill in the H's. Okay, this one's full. It had like this double, single, and single makes it have 4. Okay, these ones will fill in the H's. Like so. Okay, so this would be propanoic acid. Okay, here give the IUPAC and, if applicable, common names. We don't have to worry about common names. We just have to worry about IUPAC names. Okay, and so this has one carbon chain, so it's methanoic acid. Okay, if you aren't sure about common names, there are some in your data booklet. So if you look up methanoic acid, I believe it's also formic acid. Again, so ethanoic acid would be acetic acid, so on like that. So, but if I don't give you the common names, you just have to know how to label them as the IUPAC names. Okay, for this one, we have a carbon chain. So this is carbon 1, 2, 3, 4, 5. Okay, so this is pentanoic acid. This one here, 1, 2, 3, 4, 5, 6. So hexanoic acid. Okay, drawing the formulas. So octanoic acid, we're going to have 8 carbon chain. It'll look like this, just with 8 carbons and then the COOH at the end. Okay, remember that, like, for structural formula, you want to draw each bond to each 8. Okay, benzenoic acid. So again, benz is for benzene. So we draw our benzene ring. Our hexagon. Okay, again, benzene has the delocalized electron, so we draw the circle. Okay, and so coming off of one of these carbons, there's only room for one bond. So it can't come off, like, you can't have a COOH group. Like, this can't be the C that has the other H's coming off. So what you have to do is, from that carbon, you'll have another carbon, which then that's where we'll put our hydroxyl group. And so that's what benzenoic acid would look like. And it doesn't matter which tip you put it on, because again, like, you could just rotate it and all be the same thing. Okay, some properties. So again, the presence of both a CO group and an OH group make carboxylic acid very polar. The carboxylic acid molecules form hydrogen bonds with one another and with water. So the solubility behavior is about the same as alcohols. Thus, the boiling points of carboxylic acids are much higher than those of other hydrocarbons, and about this similar to alcohols. Multiple hydrogen bonds is possible, which increases the melting points and solubility in water of these compounds. So comparing kind of butane, okay, it has a boiling point, okay, negative 0.5 degrees Celsius. So at room temperature, butane is a gas. Butan 1-all, 117, so it's a liquid at room temperature. And then butanoic acid is even higher than that, okay, because of those stronger bonds. So it's a little stronger than the alcohols. And yeah, 165. Next functional group is the esters. So the ester is a hydrocarbon derivative that contains the functional group. Looks like this. So we have our carbon double bonded to an O, single bonded to an O, just like carboxylic acids, except instead of having an H here, we're going to have basically, it's called like a R group, which is like just a group of carbons. Okay, and so like a chain of carbons. We don't know how long that chain is, but like it can have a whole bunch of carbon, and then each one would be bonded to the proper amount. There's also a chain of carbons coming off here. So the general formula for ester is RCOOR prime. Okay, so the R represents a hydrocarbon or just a hydrogen atom. You could just have a hydrogen atom here with the R. So that's possible. Okay, but R prime, so over here, okay, it can't simply be a hydrogen atom. It has to be at least one carbon, because if you put a hydrogen atom there, it's no longer ester, it would be a carboxylic acid. Okay, so you're going to have two branches, or like two groups of two carbon chains coming off of this hydrocarbon, or this ester group. Okay, so when we name it, we have to kind of know which one we're going to use. So to name the ester, you must think of a combination of a carboxylic acid and an alcohol, because the names of those compounds are used to name an ester. So really, the alcohol would be coming off this side, and the carboxylic comes off this side. Carboxylic acid, sorry. So again, identify the root. Okay, so identifying the root, part of the ester contains the CO group. So basically the root for esters comes off this side. Okay, so again, the root will be the kind of the main part of the name. Okay, so to determine, so this part comes from the acid, and the root name of the ester is based upon the name of that acid. Okay, so determine the parent name of the acid. So again, coming off this side over here. Okay, the suffix, okay, so that's how we kind of finish the name off. We remove the oic acid from the name of the parent acid and replace it with O8. And so, and then the prefix would be the alcohol, like that comes off this side, our R prime side. Okay, so to form the prefix, consider the part of the ester associated with the alcohol. So ignore the oxygen atom and use only the alkyl group. Identify the name of the alkyl group, and the name of the alkyl group is the prefix for the name of the ester. Okay, there's always a space between them, between the alkyl group and the name of the ester. So the example here, okay, oh, whoops, want that. Move this out of the way. Oh. All right, well, I'll do another example on the next page. That'll be a little bit better. All right. Okay, so for this one here. Okay, so again, our ester, which is over here, esters are formed by adding an alcohol to a carboxylic acid. Okay, and the way we name them is we take whatever acid we had, that's going to be over here as our root name. Okay, and then whatever alcohol we had became the prefix. Okay, so butanoic acid becomes butanoate, and then ethanol becomes our ethyl group. Okay, and if we're just naming them here without seeing like the actual formula and how they got there, okay, again, just start here. The group coming off over here, whoops, need the writing, there we go. Okay, so the group coming off here, that's our parent chain. So it has 3 carbons, so it's going to be propanoate, and then we have 1 carbon coming off here, so we have methyl propanoate. Okay, so methyl propanoate. Okay, this one, we have 1 carbon coming off, okay, our ester group. And then over here we have 3 carbons, so this would be propyl, because that's the prefix. This is our root name, methanoate. So propyl methanoate. Okay, if you're drawing the line structural form equation, write the IUPAC name for the ester formed between the reaction of propan-1-ol and benzenoic acid. So we can start benzenoic acid. So we have benzene. Oh. Okay, that's our benzene ring. Coming off of that is our acid group. So double bond to O, single bond to O. Okay, if it was an acid, it would just have an H here. Okay, benzenoic acid. Yeah, so because we're bonding it with this propane, the propane bonds over here, propan-1-ol. So prop is 3 carbon chains, so we're going to have a 3 carbon chain. Whoops, we forgot we're going to do a line structure. Okay, so we have There'd be one carbon there, carbon there, carbon there. So this is what it would look like, the reaction. Like this would be the product if we reacted these two. Okay, and then we had the name for it. Okay, would be, we start here. This is our prefix. There's 3 carbon chain. Okay, so it's going to be propyl benzanoate. Propyl benzanoate. Oops. Not sure what's happening here. There we go. Okay, physical properties. If I can zoom out here and figure out how to use this. Let's see if this, there we go. At least we can see a little more of it now until I mess it up again. All right. So physical properties. Do you have esters? So again, they have the CO group, which makes them somewhat polar, but they're missing that OH group. Okay, so there's no hydrogen bonds. Okay, so their boiling points are lower than alcohols and carboxylic acids. Okay, but they are somewhat soluble and somewhat, they'll have a higher boiling point than the corresponding carboxylic acids and alcohols.